Hi, everybody, and welcome to part 2 of our notes. And today we are going to actually finish up the unit by talking about liquids and solids. So for liquids have a set volume, but will take the shape of their container. And we're used to that. We deal with liquids all of the time. All right, whether it's a water bottle, a glass of water, all right, a test tube of water, it's going to take the shape of whatever that container is. Particles and liquids flow past each other. That's how you can kind of visualize their motion, all right, as opposed to gases, which is just kind of motion all over the place. Okay, the intermolecular forces in liquids is much stronger than those of gases, allowing them to stay in closer contact. All right, and one way for us to judge how strong the intermolecular forces are in liquids is to look at what happens when liquids do turn into a gas. So let's get some terminology down. All right, so what are some things that can happen to liquids? Well, when you convert a liquid to a gas, all right, otherwise known as vapor, if something is typically a liquid at room temperature and we've turned it into a gas, we usually refer to it as vapor, like water vapor, okay? But that is called vaporization, and that makes sense. Right, so that's what vaporization is. Okay, now vaporization is a broad term, and it's just simply turning a liquid into a gas. Vaporization can occur in a couple different ways. One way is what's known as evaporation. All right, and we have certainly heard of evaporation before. All right, this is vaporization that only occurs on the surface of a liquid. All right, so water actually evaporates all of the time anytime you have an open container, but evaporation is only occurring on the surface. Okay, and we're missing a word here, and this is pressure. Okay, so the evaporation of a liquid in a closed container causes what is known as vapor pressure, and that's what we are going to take a look at and talk a little bit about right now. So let's look at vapor pressure. All right. Okay, so, all right. So what's going on here? Here's my flask, and here we go, closed container. So, I've got the little top on there. And I have a liquid down here at the bottom. All right. At first, molecules on the surface of the liquid that have enough kinetic energy will evaporate. And this actually happens really at almost any temperature for any liquid. You're just going to get more kind of depending on the type of the liquid it is. So you're going to have some of these liquid particles turning into a gas. As soon as they turn into a gas, all right, they will start, after a time, they will hit the sides of the container, causing vapor pressure. This will also cause some of the molecules to condense. All right, so it's going to cause some of them to condense, okay, and turn back into a liquid again. So what's going to end up happening, all right, we have our liquid, it's turned into a gas, it's going to hit the sides of the container, that's going to give us some vapor pressure, something we can actually measure. Some of those particles that hit the sides of the container are actually going to condense and turn back into a liquid again. All right, eventually the rate at which the liquid evaporates and condenses will become equal. And when this happens, this is an example of what we call a dynamic equilibrium. And remember, we have talked about equilibrium before when it came to chemical reactions. And anytime we talk about in chemistry an equilibrium, it means that the rates of two opposing things, in this case, evaporation and condensation, are the same. It does not mean that you have the same amounts of each. Okay, so the same idea holds true for this. All right. When a liquid is heated to a temperature at which particles throughout the liquid have enough kinetic energy to vaporize, all right, so now we are talking about a new situation. We've added more and more energy, all right, and now we have enough for all of the liquid to vaporize. We say that the liquid is boiling, okay, so the liquid boils, okay. Boiling occurs, and this is an important one, please put big stars by this one. Boiling occurs when a liquid's vapor pressure is equal to atmospheric pressure. So when the vapor pressure is equal to atmospheric pressure. So remember, we talked about the boiling point of water being 100 degrees Celsius in our last set of notes. It's actually only 100 degrees Celsius when you are at standard pressure, which is 101.3 kilopascals. Again, for where we live, we are at sea level, and so that means that's typically what our air pressure is. So that is the pressure we deal with. Okay, so liquids can boil at any temperature. It all depends on the atmospheric pressure surrounding it. Okay. What we talk about, why we say the boiling point of water is 100, is because that is what's known as the normal boiling point. Okay, the temperature at which a liquid boils at standard pressure. Remember, standard pressure is 101.3 kilopascals, or 1 atmosphere, or 760 millimeters of mercury, just depending on what you are dealing with. All right. One way for us to look at what's going on with the vapor pressure of liquids is to look at what's known as a vapor pressure curve. All right. It shows the relationship between temperature, okay, so between temp and vapor pressure. Now, this isn't a great copy, but you have a better looking one in your notes. You're always going to have temperature on the x-axis, and you're going to have vapor pressure on the y. All right, and here I have 4 different liquids. Okay, so propanone, ethanol, water, and ethanoic acid. And it is showing us the vapor pressures, all right, at these different temperatures. Now, what you also have is this dotted line. And if you notice this dotted line, they're telling you is at 101.3 kilopascals. So where this hits this dotted line would be where we would have our normal boiling points for those different substances. Okay. All right, that's why that is there. Now, again, we can have, let's just take water, for example. We can have water boiling at any of these points, but the pressure is going to have to change. All right, so if I wanted to know, for example, what is the normal boiling point of ethanol, I'd go to my dotted line, I'd go over to ethanol, and then I'd go down, and I'm probably right around 80 for that. Okay. Another way that we can use these graphs is you can compare the intermolecular forces of these different liquids. Here, ethanoic acid has the strongest intermolecular forces of these 4. How do I know that? It has the highest boiling point. It takes the most energy to turn these liquid particles into a gas. All right. Whereas propanone over here would have the weakest intermolecular forces. All right, you're going to get some practice with these vapor pressure curves, and we will look at those further in a little bit. All right, we are going to end talking about solids, okay? Solids have a fixed volume and shape. All right, and again, we're used to dealing with solids in our everyday life, so we know what we mean by that. Solids have particles that are very orderly arranged. They do not have the ability to kind of flow past each other. They are in a set pattern. The particles, however, are still moving. We say that they are vibrating around a fixed point, so very, very limited motion. Most solids form crystals, and if you were to go on in chemistry, you would study a little bit more specifically the different types of crystals that there are. And crystals are very orderly arranged, repeating 3-dimensional patterns that are called crystal lattices. Okay, now, the last thing we're going to talk about is changes of state, and we're going to look at one more graph that's going to allow us to see these changes of state. But first, let's just get a little terminology down and make sure that we are all set with these. All right, so melting and freezing, we know what that means, right? If I'm melting, all right, I'm going from a solid to a liquid. All right, or if I'm freezing, I'm going from a liquid to a solid. Vaporizing and condensing, we already talked about this, and this is liquid to a gas or gas to liquid. Now, 2 that we might not be as familiar with is what's known as sublimation. And sublimation is where you go directly from a solid to a gas. All right, and the best example of this is if you've ever played or seen dry ice, all right, which is solid carbon dioxide. That goes directly to a gas without going through the liquid state. Deposition is just simply the opposite of sublimation, and this is when you go directly from a gas to a solid. All right. One more just little piece of information you need to know before we look at the next set of graphs is what's known as STP, which stands for standard temperature and pressure. All right, we already know our standard pressures, right? So 101.3 kilopascals. Standard temperature, all right, is 0 degrees Celsius, which remember is 273 Kelvin. All right, that's going to come up a lot, and we will talk about those in some of the problems that you have. So please remember standard temperature and pressure. All right, so we are going to look at our last graph, and this is going to take a look at all three of our different states of matter. This graph is called a phase diagram, and I do not have a color printer. Usually these are, when you look in textbooks and things like that, these are in color, and you're gonna have your three different states of matter in different colors, so they look really pretty, but this one's not. Anytime you look at a phase diagram, the area all the way to the left, so this whole area here, is going to be your solid. The area all the way to the right and typically down a little bit is going to be your gas. So that's gas over here. And then your area in the middle is your liquid. So just kind of to give you an idea as to what's going on there. This line right here between our liquid and our gas, this is the same line we saw in our vapor pressure curves. But a phase diagram also has the melting freezing points and the sublimation and deposition point. You have temperature on the x-axis, you have pressure on the y-axis. All right, and just a couple little pieces of terminology. You have what is known as the triple point. And your triple point is right here where these three lines come into contact with each other. And this is the temperature and pressure where all three states exist for the specific sample. So you could imagine if you were looking at water for this would kind of look like kind of blurry ice water, like steamy ice water, because you would get solid, liquid, and gas all going on at the same time. All right. We also have here what is known as the critical point. Critical point. And this is the temperature and pressure where phase boundaries cease to exist between liquids and gases. So up here, right, as soon as I go beyond this, you actually can't tell the difference whether you're dealing with a liquid or a gas, all right? We won't deal with that a whole lot, but it is something to know about, all right? So with this graph, you're gonna be able to answer all sorts of different questions. I can give you certain temperatures and pressures and ask you what's going on. What's going on as I move from this area to this area? All right, well, as I go from my solid to my liquid, I am melting, right? As I go from my liquid to my solid, I am freezing. Okay, so all of those different things, and we're gonna do some practice with phase diagrams so you can feel very comfortable with them. All right, have a great day, everybody.